Hello everyone. So today in this video I'm going to review a paper which focuses on stochastic optimization for robot motion planning. So more about this in the next slides. So this paper tackles two fundamental challenges in humanoid robotics, which is posture generation and trajectory optimization. These problems arise whenever we want humanoid robot to navigate complex environments, like let's say damaged garage. What makes this especially interesting is that while we human naturally solve these problems when walking around obstacles, getting robots to do the same is remarkably complex. Why it's challenging, if you may ask? First is non-convexity of the problem. The optimization landscape has many local minima where all algorithms usually get stuck. For instance, when trying to move an arm around an obstacle, a simple optimization might keep trying to move through the obstacle rather than finding a path around it. Second is higher dimensionality. A robot typically has 30 plus degrees of freedom. Planning movement means solving all these dimensions simultaneously while maintaining all constraints. For trajectory optimization, this multiplies by the number of time steps, which is a huge computation to do and solve the problem simultaneously. So, traditional algorithms used deterministic methods such as sequential quadratic programming and some of other work such as CHOMP, which was in 2013, then STORM 2011, and TRAJOPT 2014. All these approaches have one thing in common, which is they often get stuck in local minima and require careful initialization. And but one thing was like none of these previous methods used deep learning community's success with stochastic optimization, and the paper we are reviewing right now actually used that. So more about that in next slides. So in the proposed solution of the paper, two major innovations have been done, which is first introduction of ISQP and second is leg opt benchmark. So in the ISQP algorithm, we are combining traditional optimization techniques with stochastic methods. And basically, we are introducing controlled randomness to escape local minima, which was a big problem in previous algorithms. And basically, we are just updating only a few subset of constraint at each iteration. So to talk about more about the math, which you can see on the right, the optimization formula captures both physical requirements and practical goals. And we are handling multiple constraints simultaneously and using the sequence techniques. So why is this advantageous, if you may ask? Then, because particularly in challenging scenarios, let's say when a robot starts in a difficult position, like having its feet in collision with the ground, the ISQP method shows remarkably better performance than traditional approaches. Specifically, ISQP succeeds in 38 out of 50 cases, while conventional SQP only manages 29 successes. This represent a substantial improvement in reliability. The speed is also noteworthy. ISQP processes each viewpoint in about zero point 0.7 seconds, making it 20 to 30% faster than traditional methods. And this is a very important when planning longer sequences of movement where time saving accumulates. Another major advantage lies in the method's ability to escape a local minima, as we talked. So, however, this approach does have several uh, advantages. We have limitations as well, such as when we find a solution, it tends to produce slightly lower quality trajectories than traditional SQP. And the authors of the paper are working on this as of now. Another other innovation was the benchmark. So before this paper, researchers in motion planning faced a significant challenge. They couldn't easily compare different algorithms because everyone used different test scenarios. Think of it like trying to compare a race cars when each one runs on a different track. You can't really tell which is better. Previous work typically evaluated algorithms on custom scenarios chosen by individuals, and it made it difficult to compare algorithms with each other. So in this Allegro benchmark, uh, the authors have introduced a standardized testing environment, a damaged garage scenario, and there is specific evaluation criteria and a comprehensive set of 50 test cases. This is similar to how ImageNet revolutionized computer vision research. So let's talk about ISQP algorithm. So here basically we are using stochastic methods, which is very common in deep learning. The algorithm's novelty lies in how it selectively updates constraint. Instead of processing all constraints in every iteration like traditional SQP, it randomly samples a subset to update while keeping others fixed from the previous iteration. The flow works like this. We take initial parameters, let's say tolerance, a penalty, and in first iteration we convexifies all objective functions. Then in subsequent iterations we randomly sample a subset of function where let's say sample batch. Then we update convexifications for sampled subset and then keep all previous convexification for non-sampled functions. Here we solve optimization within trust region only using updated convexifications. We also check if constraints are satisfied, like if yes, exit, if no, continue iterations. The selective updating approach helps escape local minima while maintaining computational efficiency. So to talk about the results, ISQP achieves higher success than traditional SQP and it's 20 to 30% faster. There are definitely trade-offs such as the solution quality is lower, but we have solved one of the biggest problem in humanoid motion planning scenario. Thank you. Thank you.